all the individuals who are retired. If you look at this proportion to this proportion, if this is larger compared to this, like every individual here, if you have a look at the number of people below and the number of people above, every working person is supporting 2 others. That's bad news for an economy. Compared to an economy where every working person has to support maybe 1.2 others, now they support 2.3 others, then it's in a society that's not well off. So in order to get around this, we have to look at the dynamic aspects. And to get a dynamic model, we have to look at the initial conditions. And so we can build a model. And if we build a model, what we do is we define xi to be the number of individuals in the first age class, and x1, and x2 to the number of individuals in the second, and x3 the number of individuals in the third. Now what we're going to do is we're going to make a simplified model. We're not going to have one being ages, but we're going to have one, so we're not going to have x representing ages, we're going to have x representing classes. So we can do this in a model. So we don't have to put in all the age classes. An age class model would say xi are the number of I-year-olds. And in a human population, you'd have to have a model that had x1 up to x100, say, if you weren't worrying about individuals above 100. But here we're going to say x1 just represents the number of immatures or juveniles in the population, and x2 represents the number of adults. And so, in a very simple model like this, we can draw a diagram that says, okay, here's x1, and here's x2. So, S1 represents the proportion of individuals that go from age class, or go from class 1 to class 2. So, these are the young and these are the matures. Then how do we get new young? The mature individuals each produce a certain number of young, which we'll call B. But of those young that they produce, a certain proportion of them die before they become juveniles. And then, of the adults, the juveniles become adults. We'll say if you're already an adult, you stay an adult. So those S2 then represents the proportion of individuals who are adults that survive to remain adults. So if I had to write down the equation for this, I would say x1 at time t plus 1. That is the number of individuals in age class who are accounted as juveniles is going to be equal to the number of adults times the number of, let's say, young that are born and that survive the initial period. So how to interpret this depends on how you look upon things. Like if individuals lay eggs, then S0 could be the rate at which the eggs hatch. The different interpretations. Having 2 parameters allows us to have 2 things going on here. Number of individuals that are hatched or laid or produced times the number that survive early processes to make it to be called a juvenile. So this is, but it acts as a single parameter because it tells us that if we've got a certain number of x2s at time t, then at time t plus 1, we'll have a certain number of x1s left. And then x2 at time t plus 1, how do they come about? Well, firstly, we have a certain number of x1s at time t, and a proportion of those survive, plus we have a certain number of x2s at time t, and a proportion of those survive. Yeah? Why wouldn't you subtract that here? Okay, because these are coming from newborns, and they're all going over. That's why there's no x1 term here. Yeah, so there's no return. It means everybody here, everybody who was an x1 at time t, became an x2, except for actually s0 of them. The x1s become x2s. That's why they're in here. None of the x1s remain behind to be added in. That's why. So that's the answer. The x2s produce a certain number of s1s. I could just call this some constant k. But actually, it turns out that it's convenient for later treatments to think of these in terms of 2 processes. That's the number of individuals that are immediately produced in terms of eggs or newborns or whatever, plus their survival rate to make it over to the first age class. Because this is like counting 1-year-olds, not 0-year-olds. So the 0-year-olds are the ones that are immediately produced, and then a proportion of them survive to become 1. And these are the 1-year-olds and the 2-year-olds. So that's why I break it up that way. But this is a very simple model. So a more complex model would take age structure into account. But the important thing about this model is that it's got 2 variables. And I can write this using what's called a 2-column notation. So I write this as x1, x2 in a column, and I put in that it's evaluated at time t plus 1. And then I can write this as a column. So all this does is it allows me to use 1 equal sign instead of 2 equal signs. So you say this is a waste of time. I can write this right-hand side here as a column, and I can write this lower one. So I've taken this and I've put it into a column notation. Big deal. Why would I do that? I mean, this is no clearer than that, is it? However, there is a process where I say, I have something that I call a vector that I represent as a column, x1, x2. And so this is this vector, x1, x2, evaluated at time t plus 1. I can write it in that way. It's not usual to write it in that way. It's better to write it in this way. But what I gain is that on this side, I can break this up into what I call a matrix, which is I write a 0 and an S0 over here, and I write an S1 and I write an S2 here. And then I write x1 at time t and x2 at time t. Now, it turns out this statement is equal to that statement if I define matrix multiplication to be this column, this row times this column, where I do it element by element. So that's 0 times x1 and s0 times x2. That would give me the first term. And then again, if I take this row and I multiply s1 times x1 and s2 times x2 and add them, then I get that row. And so I actually turn out and I write this like this. X, and I underline it, and I say this is a vector of 2 elements, and it's equal to this matrix, which I'm going to call L, times this vector x, evaluated at time t, where x has 2 elements, x1 and x2. Now, there's no big advantage in 2 dimensions to do this, but it becomes a big advantage in n dimensions. So we can explore these ideas in terms of using matrices and matrix vector multiplication to represent these kinds of models. And it turns out that there's a theory of matrices that really helps us understand how populations grow from the properties of this matrix L, which is given by these 4 elements over here. So I'm going to discuss this kind of representation because this theory is a very powerful theory for understanding what happens when your models are represented by vectors, not just with 2 elements, but sometimes with 10 elements or 20 elements. So in some models, I'm not only interested in two classes, I'm interested in 10 or 20 or 30 classes. So when I'm interested in 10, 20, or 30 classes, I don't want to write out 20 equations here. I want to write one equation. So I write the equation like this, but then I talk about the structure of that matrix L that represents writing it out as 20 equations. Does everybody understand that? So that's what we'll talk about in the next lecture.